Hey there, everybody. Good afternoon. I hope you're all doing well. Today's problem challenges our assumption about springs being massless. Now, that's a helpful assumption to use when you're first learning the concepts, but when it comes to the real world, obviously that's not an accurate claim to make. Our problem has two parts. For the first part, we're going to derive an equation for the kinetic energy of this spring by breaking it up into small pieces and integrating along its length. In the second part, we'll use the equation that we derived to answer everything here that's left. Let's get started. The problem description tells us that we can assume the speed of points along the length of the spring varies linearly with a distance, called lowercase l, which is measured from this fixed end. If we convert that jargon speak to just plain English, here's what it's trying to convey. When we release this spring from being stretched or compressed, it doesn't really matter which, the speed of a particular chunk of the spring will depend on how far away it's located from the base. The further you move away from the base, the faster that chunk of the spring will move. If we want to codify that statement mathematically, here's how we'll do it. This says that the velocity of a chunk of the spring at some length away from the base, which is lowercase l, is equal to the ratio of the maximum speed found at the end of the spring to the entire length of the spring, multiplied by how far away from the base the chunk is located. Using this visual example on the left, I've picked a random length for lowercase l, which is about halfway along the length of the whole spring. With this equation in mind, that means that the velocity at this section will be about half the magnitude of the speed found at the end. So that's how that one works. There's one more equation that we'll need. This one says that a tiny chunk of the spring's mass is equal to the ratio of the entire mass of the spring to the entire length of the spring, multiplied by some tiny little displacement along the spring's length measured from the base. Let's get a visual of what these mean as well. If I break the mass of the spring up into tiny even chunks like this, then dm is going to represent the mass of one of those chunks, like this one. And dl is just the length of that tiny little chunk. With these two equations known, here's what we're going to do. We'll set up an equation that integrates the kinetic energy of each tiny little chunk, starting from the base of the spring all the way to the end. This form of equation is pretty similar to the kinetic energy equation that we're familiar with, 1/2 mv squared, but we're dealing with small chunks of an object here instead of one giant object. And each chunk has its own particular speed. So instead of m, we'll use the mass of a chunk, dm, and instead of v, we have the speed of each individual chunk, v sub l. Again, the idea is to integrate this expression along the length of the spring, and to do that, we'll have to substitute our expressions above for dm and v sub l. Let's do that on a fresh slide. First up is substituting dm for m over capital L times d lowercase l, like this. Now the integration variable is correct, since lowercase l can range from 0 to the entire length of the spring. Next is to substitute v sub l, which also depends on lowercase l. We have everything that we need, but the pieces are just all over the place. Let's rearrange this and fix it up a bit. The 1/2, mass, spring length, and speed of the spring found at the end can all be factored out of the integral because they're constant. The only thing that we need to integrate is lowercase l squared, and that's not hard at all. When we do that, we'll get lowercase l cubed divided by 3, and we want to evaluate this from the base of the spring to its full length. Our result is all of these constants out front multiplied by capital L cubed divided by 3, and the l's will cancel out, and the 2 and the 3 in the denominators will multiply together, resulting in our answer, mv squared divided by 6. That's it for part A. Now we're ready to tackle the rest of the problem. In part B, we're going to calculate what the velocity of the ball is before factoring in our derived equation that we just worked for. That way we can compare the results. We'll use the work energy theorem here to equate the work done by the spring to the kinetic energy of the ball. We can eliminate the initial velocity variable right away, since the ball is just sitting there motionless before we launch it. The work done by the spring on the ball is that 1/2 kx squared quantity, and since there's a factor of 1/2 on both sides, let's get rid of that as well. If we divide both sides by the mass of the ball and take the square root, we get our expression for the velocity of the ball as it reaches the uncompressed length of the spring. Plug in the numbers, being sure to convert centimeters to meters along the way, and you'll get the following. We used some values with 2 significant figures to get here, though, so let's chop this 6.14 down to 6.1 meters per second. And that's our answer to part B. Now for part C, here's where the kinetic energy of the spring comes into play. Some of the work done by the spring goes into the ball's kinetic energy, and some will go into the spring itself. The final velocity of the ball and the end of the spring will be the same, and that's the variable that we want to solve for. We can start by factoring that quantity out on the right-hand side, and what I'd like to do next is get a common denominator between these two masses in the parentheses. So let's multiply the mass of the ball by a special form of 1. So when we incorporate that, the denominator will also be 6. There's no reason to keep these fractions separate anymore now that they have the same denominator, so let's join them together and bring the full equation back into the picture. I'd like to get rid of this 6 in the denominator on the right-hand side, so let's multiply both sides by that value. On the left, 6 divided by 2 is just 3, so we'll have 3kx squared following that step. All that remains is to divide both sides by the sum of masses in the parentheses, and then take the square root of both sides. Go ahead and plug in the numbers, grab your result, and truncate to 2 significant figures. Part C is now done. There's just one last thing to do. We need to compare the kinetic energies of the ball and the spring, so let's go ahead and start with the ball and grab the extra significant figure in the velocity from before, so we don't end up rounding twice and going over what the answer should be. The mass of the ball is this 0.053 kilograms, and when we multiply everything together, we get about 0.4 joules when using 2 significant figures. For the spring, it's the same process. Just make sure you're using the 1/6 coefficient and the spring's mass instead of the ball's. When multiplied together, we'll get a slightly larger amount of energy, about 0.6 joules. Time for a quick recap. In part A, we broke the spring up into equal chunks of mass and realized that each piece has a different velocity as we move away from the base of the spring. When the kinetic energy of each piece is integrated, we find that the kinetic energy of the whole spring is 1/6 mv squared. In part B, we treated the spring as massless and calculated the kinetic energy of the ball as normal, and we arrived at this 6.1 meters per second speed here. Part C made us include the kinetic energy of the spring, which robs the ball of some of its speed, and both objects moved at a rate of about 3.9 meters per second, which is about 35% slower than the massless spring case in part B. Finally, in part D, we calculated the kinetic energy of the ball and the spring when moving at this speed from part C, and that gave us 0.4 joules for the ball and 0.6 joules for the spring. Thanks for watching, everyone. I hope this helped. Take care.